Hi, my name is Tony Kanak from Dayton, Ohio, and I'm going to be giving you a guided tour through some of the basic science of sound. This will include frequency, amplitude, propagation of sound waves, and timbre. This is in conjunction with the first several lectures taught by Mr. Loudon Stearns in Introduction to Music Production Week 1 on coursera.org. First, let's look at sound as a wave. The first thing we should understand as listeners is that sound waves are longitudinal. This means the direction of propagation is parallel or the same direction as the sound. This is different than a transverse wave, which is depicted as a sine wave, typically. But for the purposes of looking at sound, we will be looking at some sine waves, which are a graphical depiction of longitudinal sound waves. Typically, sound propagates through air, although it also propagates through other materials, such as wood, metal, and water. The rate at which it travels through these different materials varies, but for our purposes, we will be looking at sound traveling through air. Other factors which influence the speed sound travels are elevation and temperature. A good way to remember the speed of sound is the approximation, 1 foot per millisecond. The first thing you should know is that sound is both compressed and rarefied. With increased pressure, the air molecules are compressed, and with decreased pressure, the air molecules relax. As the sound wave travels through the air from source to ear, the wave is alternately compressed, then rarefied, compressed, then rarefied. This is like the action of a slinky that is pushed lengthwise. Some of the effects associated with sound propagation are echo and reverb. Now we can turn to amplitude. Amplitude is the strength of a sound, or qualitatively, the loudness. This is typically measured in decibels. There are two important ways of measuring amplitude. The first is decibel sound pressure level, or dBSPL. This is the amplitude or height of the sine wave. The normal range of hearing goes from 0 dBSPL to around 120 dBSPL. Above that, we reach the pain threshold. The second way we measure amplitude is through dB full scale. This is a measure of the computer's strength, with 0 dB full scale being the maximum amplitude. The faster the processor, the lower the minimum amplitude can go. Furthermore, an instrument carries a dynamic range. This is the range from the noise floor to distortion levels. The effects associated with dynamic ranges are gates, expanders, limiters, and compressors. These affect the amplitude of the sound. Sound also has the property of pitch, or quantitatively speaking, frequency. This is measured in cycles per second. The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. The range of hearing for humans is roughly 20 Hz, or cycles per second, to 20,000 Hz. Other animals have different hearing ranges. Frequency is closely related to timbre, or sound quality. Different instruments carry different timbres. This is not only because of the different string lengths and thicknesses, but also due to the type of instrument. Many instruments have an overtone series or a series of higher harmonics. For instance, stringed instruments vibrate in multiple harmonic frequencies at the same time. This gives us a richer spectrum of tones that augment the timbre of the instrument. Filter effects also affect the timbre. Thank you for considering the aspects of sound with me. I hope it has been a challenging yet rewarding experience. Continue to stay in touch with the tune.